Hello again, everyone. So now in this session, the goal is to do a little bit of a tutorial of microwave lock-ins, introducing what they are and what they can do. And we will also get a little bit hands-on with the instruments here I have on the desk. They're running, actually, you might hear them as well. Their fun is working. So, but I would like to quickly start with a short presentation with few slides only, and with a focus on microwave lock-ins. Why do we need microwave lock-ins essentially? And I like to really step out a little bit on looking at the toolbox that we actually provide for scanning probe microscopy. And as we already know, like these kind of probes we are working with, and I like to see them as some sort of a sensor, right? So we are trying to detect something that is on the surface in one way or another. And to be able to do this, we need to have some control software, control electronic, and a toolbox that is flexible enough when we actually design new sensors, essentially, new kind of ways to probe what we like to achieve. So in the end, SPM is actually one of the techniques that brings a lot of power detection techniques into nanoscale, right? And this is done by, in many cases, adopting one of these sensors. What they provide is, for instance, near field enhancement, right? When you approach the tip, you can actually go beyond the fraction limit if you would try to do in optical ways or another. And this is also the case for microwaves as well. So if you would try to measure microwave directly by a transport measurement or so, that wouldn't be that easy to get the resolution we need. But in the end, providing some sort of a microwave waveguide and the way to couple to the surface with the tip, it actually allows us to achieve that. So we can actually do reflectometry, as we also heard in the previous presentation. And beyond that, we can also put a little diamond there and actually have measurement that is sensitive to the spins, or do magnetometry actually in nanoscale. What is important, of course, that since these nano devices are small, they are embedded in a noisy environment, we need to be able to recover these signals, right? And that's where the Lockin actually comes into play, where we can do these measurements and really recover weak signals from the environment. And this is not always enough. We also need to pair it with resonant enhancement by working with resonators or so, where Lockin is actually quite helpful because we can tune it to the right frequency to be able to benefit from that as well. I'd like to continue a little bit of the background or a brief introduction on Lockin detection. It might be hopefully refreshing for some of you, and maybe to a few of you some new insights. As I mentioned, it's a sensor, some sort of a sensor that transduces whatever it interacts with into electrical signals in a very weak signal like that. And we try to actually get some sense out of this signal. So what Lockin does is it tries to measure the signal in a certain frequency. And if you actually draw the sine wave on it, you can actually see already some information actually hidden in the signal. And that's what Lockin actually provides. Typically, it is a two-step process. First is we need to mix the signal that we are trying to measure with a reference signal to ensure that we are actually measuring at the right tone, and then filtering out everything else. So that's done by the low-pass filter. But and yeah, in the end, you can actually picture in the frequency domain, Lockin is sort of a bandpass filter. It boils down to a very narrow bandpass filter in the end, and you can actually have multiple of these in a single instrument if you have a digital system, right? It's very easy to scale then. Everything is done digitally, and then these kind of Lockin amplifiers becomes beyond just a Lockin, but an entire test time measurement setup in the end. So it offers much more. We can have, as I said, multiple of these units in one place. It also offers time and frequency domain tools in one box. And you can also put feedback controllers, so on and so forth. I mentioned low pass filter. So the filter bandwidth is very important for Lockins. So we need to always find the right compromise between how fast we can measure and how much noise we actually filter out. And this is actually defined by the filter bandwidth. If you look at the frequency domain picture here, I hope you can see the pointer. As a function of frequency, we see this filter rolls off eventually, and how narrow this filter is essentially tells us how much noise we actually cancel out. So if you use this filter, you will not be using, we will not be capturing signals beyond that. But it also has an impact, of course, when you narrow it down, the measurement gets slower. You can picture it as an averaging, you average more. And it's reflected here. So if you look at the blue curve, that was the narrowest, then the time response gets slower. So if you look at in an actual signal properties, this will be a wider low pass filter where we see some features, but there's a lot of noise. And then we narrow it down, and then you start seeing much better. But if you narrow it too much with your, depending on the time response of the system we are looking at, you start smearing things out, as appears in this plot here. So that's why it's always very important to have a tool set that you can look at the signal, look at how it behaves, and then tune it to the right parameters. And that's very important for Lock-in amplifiers. So in Zurich Instruments, what we do, we provide a bunch of different instruments. So here we actually see it as a function of frequency, starting from the frequencies that cover few hundred kilohertz to megahertz. And then we have the HFLI that is up to 50 megahertz. And these instruments actually serve for various different applications. UHFLI is a sort of a workforce that is very flexible instrument that brings its function to 600 megahertz. And recently we introduced these two fellas, the GHFLI and SHFLI Lock-in amplifiers, as Roman also was mentioning. But actually very important is that you can have a very good hardware, but if you don't have a good software to control it, it becomes in the end not very useful. So this is what we actually provide with our user interface LabOne. And it provides a whole bunch of functionalities, all the tool set that you need to actually look at the signal, to take the right decisions and set up the experiment in the right way. Now let's quickly focus on how these two Lock-in amplifiers actually work. And actually, I would like to focus on the SHFLI a bit more. It's again a filter like that we mentioned, but to be able to achieve the high frequency, we also work with a second frequency that's called center frequency. It's actually a mixing scheme, but we try to limit the exposure for such a complex scheme to the user, right? And we like to simplify things as much as possible. So in the end, you need to set two frequencies with the instrument, which I will actually show with the instrument as well. But we can also achieve, while we have the high frequency capability, we can also go lower in the frequency regime as well. So we will be talking about an oscillator frequency that sets where this filter is at, and also the center frequency in a bit. So let's get hands-on with the instruments. And you please interrupt me anytime if you have a question or so, we can quickly discuss. There's not much time, I need to rush through a little bit, but if there's something not clear, please let me know. We can also discuss later in the afternoon. We have another longer Q&A session. So now I need to stop the screen share for a second to be able to go to the user interface. I hope this works fine. I have some stuff that's a little bit on the way, but it should be all right. Let's move them down. All right. So what I have here is the two instruments actually connected. So we actually, the interface lists them already. And I'm only connecting to SHFLI right now. We can connect multiple instruments and work in the same user interface together. And at the moment, there's a lot going on. I like to walk through you a little bit what's happening. So what is the most important part is, of course, the initial part. Initially, we need to set up the hardware. That's basically how the signal inputs and outputs are configured, right? And this is where we actually set the signal inputs. So this we call the Lockin tab that configures everything you need to work with the instrument. Here we have the signal inputs. We have two of them. They are there in the front panel. You can also see. And you can set the input-output ranges and a bunch of other settings as well. And here we have the output settings. That's where we set the output range for 2 channels again, one of the 2. And you can assign multiple of oscillators with a certain amplitude. So what's happening right now is that between the input 2 and output 2, I have just a loopback cable, just this cable. It's a short RF cable, just to see what I am generating actually. And input 1 and output 1, I have an RF resonator that we will look at in a second. So I like to first look at the input to output 2, where we actually configured here. We are in the baseband mode, so we don't actually do a mixing. And what that means is that the frequency we are working at is whichever oscillator I select. So in the instruments, we have a bunch of oscillators. Here you see 8 of them listed, and you can configure them in a certain range. And then this signal, essentially, when you activate the output, which will be here, will drive this signal. Now I should be seeing actually a 100 megahertz signal with 100 millivolt peak voltage, and scope is essentially also looking at signal input 2 here, is showing us this signal. Now I can look at its FFT as well. So this will be our peak. We can also combine multiple signals and look at, for instance, their beating. Yes. Yes, thank you very much. So now we have more of these tones. Now this is how the baseband works up to roughly 800 megahertz or so. And after beyond that frequencies, we need to go to the RF path. So you can actually see here the frequency range is limited to that 800 megahertz, as I mentioned. We can do that by just clicking here. Now, actually, also in the frequency domain, you can see how things changed. We are now having a center frequency of around 1 gigahertz. We can tune it, let's say maybe 4 gigahertz roughly. And then this 4 gigahertz is our center frequency, which provides us this gigahertz window that we are measuring at. And then we are using another 100 megahertz oscillator that is summed up with the center frequency. Actually, you can see the final frequency here. That is the tone we are generating. And then this is also being sent out to the output 2, and that's the tone we are seeing. So the 0 in this plot would correspond to the center frequency, right? Plus 100 megahertz, that's where our tone is. And again, we can again mix a bunch of these and then see all the other tones. So this is in the end how roughly the front ends work. And you can set it up, you can look at the scope, what you're actually doing. It's very actually useful when you configure things. But now we can look at the demodulators. So here, this block here is where we configure the demodulator itself. Now, first demodulator, we have 8 of them, and you can look at them row by row. So the 8 demodulator is now looking at signal input 2, which was around 4.1 gigahertz. And here, as I mentioned, low pass filter is very important parameter. This is where you set this up. So it's at the moment 300 kilohertz. And then we enable the data transfer. So now the demodulator is actually sending us the data, which we can look at in a numeric way. That's basically how it appears. That's sort of the RMS voltage that we expect to see and the phase. But it's a little bit boring. Just looking at numbers these days, we can actually plot them in the plotter as a function of time as well. And then we can do a bunch of statistics, look at the noise at this measurement or so. So this is roughly how you configure and how you interact with the demodulator in the first few minutes. Now I want to actually go back to the resonator. So this is a cavity. It's an RF cavity. It has a resonance around 3.7 up to like few other resonances, few other modes that goes up to 8 gigahertz roughly. And the point would be characterizing this device. For that, I still want to use the first demodulator for simplicity because it's already set up. And I need to change it to the signal input 1. And now the signal actually we are looking at should come from the resonator measurement that has been done in the input one. What we are doing is again using the output one to generate that signal that corresponds to, at the moment, the center frequency 1 gigahertz plus 100 megahertz. That's the signal we are looking at. Now, what we want to do is to sweep the frequency to basically characterize this device. I will pull in the sweeper tool. You can actually use all these tools at the same time together, that you can look at what's really happening. And that's quite useful, actually. So the sweeper is a tool that allows us to sweep a bunch of parameters that is available in the instrument. That could be frequency, but in this case, we want to do a rather wide sweep that will go beyond the 1 gigahertz center frequency that I mentioned. So for that, we also have a possibility to do this in this multi-band mode, as we call it. And then you roughly set the frequency range you wanna sweep. And I want to do that around 3 gig to 8.5 gigahertz. And you can select number of data points and then click the measurement. Now the instrument is actually automatically adjusting the frequency and measure, average, and even tune the low pass filter settings to the measurement we need. And we actually captured already resonance around 3.7 gigahertz, and a few more will come as well. And at the same time, we can actually look at the phase. Now, what we will see is a bunch of oscillations around pi and 2 pi, because we have a very long cable. We are sweeping very broad frequency range. There are lots of delays, right? And then you will basically always see pi wrapping around pi minus pi. But what we have is actually a tool in the GUI already. You can unwrap this. So basically, I will sweep again, and we will see actually how this phase decays. For that, the best will be having a few more data points actually to get the best result out of it. Of course, when you add more data points, it gets a little bit slower. What we can also do is, I didn't do that in advance, but we can actually upload a couple of previous measurements directly in the GUI to actually look at the signal itself. So this is this file here. Did I manage? Yes, there we go. So you see these two loaded measurements. I will stop the sweeping now, and then try to look at the two. Okay. My laptop is a little bit stuttering. Sorry for that, because I do screen share. So you see that. All right. So I actually have uploaded two measurements to demonstrate one thing. So this measurement is essentially shows a relatively flat amplitude versus almost linearly decaying. So this is log scale, linearly decaying phase. What I did for this measurement was I took out the resonator and connected this cable just to measure how this network is actually behaving, right? So this is our reference measurement. I can take this reference measurement to here as the reference and activate that. And this will then allow us to see the measurement I did earlier in a bit better form, I hope. For some reason, I don't see it now. All right. That's our reference. Let me just load the measurement again, just to make sure if everything is all right. There we go. So this was the original signal actually without the reference already. You see all the peaks already there, and this is the phase delay that was with the resonator in. Again, I use this as a reference. I can load it again, and then click the reference mode, and this is exactly what I wanted to see. You see a whole bunch of resonances, and again a drifting phase. But at each resonance, now we can actually capture how the phase delay looks like, which we should expect something around like a pi change, right? It's because this is just a linear resonator. So this is what you can do in a broad sweep. Now, if you want to characterize a certain mode a bit better, what you can do is you can zoom into one of these. Actually, you can of course sweep again. But what I like to do is I like to keep this measurement because I can always refer to it. I don't need to rewrite it or reconfigure the sweep that I did this measurement. I can just pull in another sweeper. And then configure the measurement again. In this case, I want it to be somewhere around 3.7. I can just set the center frequency to be around 3.7 gigahertz. And instead of sweeping center frequency and the oscillator together, I can just sweep the oscillator to do this measurement once more. Let's maybe put minus 100 mega to 100 megahertz. And then sweep it. And here you see we only now sweep this frequency and capture the response. Yeah, thanks. Thanks. Is it still doing it? Okay, it's doing it. There's a bit of a delay when I click and something happens right now, so please bear with me. You see actually the instrument is working. There we go. And because we see it a bit weird, because it is in log scale somehow here. And I want it to be linear. We can zoom in. There we go. Now, this is our nice resonance, and we can also activate the second plot. Come on. There we go. Second plot to capture the same. What I did forget in this sweep was I didn't click to the phase unwrap again. So we see the phase jump right where we had the resonance actually. So now we can zoom in a bit further. And let's say I actually want to sweep within this range. I can click this button. It will take this new frequency range as the parameters to sweep, and you can start sweeping again. And after a few seconds, we will see the nice resonance. And let's do a quick fit to this to get the parameters. Okay, let's not look at the previous sleep as well, just focus on the last data. So you see this dashed line, that's actually a resonance fit. It's a Lorentzian fit, it's a very, very brief Lorentzian fit. And in the math tab here, you see actually the parameters, quality factor, and all the necessary parameters that we need. Now we can park the Lockin to be at the peak of this resonance and measure at this frequency, for example, which we can do. So the center frequency is around 54 megahertz or so. So not center, the oscillator frequency. And in the plotter, we will start getting this signal. Yeah, it's basically the time trace of this signal. Yeah, so this is basically what you can do. It's again, my computer stutters. It's super warm now. I hope it survives. But yes, so basically what we can do with the sweeper plotter and the scope all working together. What I want to show as well is that how we can actually automate this measurement in the API. So this is a Jupyter notebook. So for our LabOne APIs, I'm using Python. That's a bit easier to show, but you can also do the same for all the other languages, MATLAB, .NET, C. We have LabVIEW as well. And for Python, of course, you can just do pip install zhinst. That works very well. And the overall architecture is, so here we are the client, right? And we can interrogate with the API using a couple of levels. So we have the high level API, the toolkit. We also have some utility functions, some helper functions that you can also use. And the core, as we call it, this low level interface. So if you want to pull data just quickly, that's useful. And then this API connects to the data server that's running on my computer right now. And this computer then control a whole bunch of instruments at the same time. And that's the power of this architecture. And how it works is we first import the required library, connect to the instrument. We also can check if the versions match, also if the software and the firmware is fine in the instrument. And what I need to provide is that's the instrument I am using it, and I have an Ethernet connection right now. And the way we then communicate with the instrument is with a node tree. So we can have a bunch of nodes like this. So we can ask the demodulator zeros sample, for example, a given sample or so. And that's what I'm going to do actually. So here I looked at how the demodulator is actually set up. And I will skip this part for the moment. I will jump back to there. And then you can ask a couple of questions. For example, we have helps, you know, if you don't know where the information is at a given node or so, you can ask to the instrument with these helper functions. But there's actually a better way that we can do it in the API. So let's say I want to know how I will activate this button. This is actually a function shown here. You can also see it in an entire log. So we call it API command log, and it's now in Python. And this is basically everything I did so far since I powered up the instrument. And you can find the last command here in this line. And you can just copy paste actually, which is quite powerful. And that's what I was explaining here. So we can skip this part. And in the end, you don't need to actually learn too much or try to get help from the API itself. You can just look at the GUI, get what you need, and then configure it. So quickly, what I would like to do is I like to get some data out from the instrument. For that, I will poll the demodulated sample for 2 seconds. And then it spits out a data like this. It's an X of the demodulated signal as a vector and the Y vector. And then we also get the timestamp and delta values between each data point. So we can compute the elapsed time. And that's what I'm going to do actually. First, I want to calculate from X and Y the amplitude and phase. And then this will be the elapsed time of this entire measurement. And then we can simply plot this data. Now at the moment we just see noise, of course, but this is basically what we can see. And then we can also plot it, of course, in amplitude and phase. Now we can also repeat the sweep measurement quickly. So we have various modules that is available in the instrument. Sweeper is one of them. You can just upload this module. This is basically a class then in Python. Set these parameters, run the sweep, and here you see the progression actually. It will take a few seconds. And then after that, we will be able to plot this. And this will be my last point.